1 minute ago, sensors beneath the Mediterranean detected movement that scientists hoped they would never see. The entire southeastern flank of Mount Etna, billions of tons of rock and magma, has shifted another centimeter seaward. The mountain is tearing itself apart. Over 1 million people live within the collapse zone. 300,000 call Catania home, a city built at the volcano's feet. What happens when Europe's largest volcano doesn't erupt but falls into the sea? The numbers tell a story no one wants to hear. Every year, Mount Etna slides 14 millimeters closer to catastrophe. Can anyone stop a mountain from collapsing? Mount Etna rises 3,403 meters above Sicily, a tower of fire that dominates the eastern horizon. This is not one volcano, but many, layer upon layer of ancient eruptions stacked across 500,000 years. The summit changes height with every major blast, growing or shrinking as magma pulses through the mountain's veins. Unlike the stable cones of Mount Fuji or Mount Rainier, Etna is fundamentally unstable. It builds upward through eruption while simultaneously tearing itself apart from within. The mountain exists in permanent contradiction, creating and destroying itself in the same breath. 4 summit craters crown the peak, each one breathing ash and gas. The southeast crater alone has produced over 200 explosive episodes since 1998. Between February and December 2021, lava fountains reached 1,500 meters high, painting the Sicilian sky in shades of molten orange. But the real danger is not what rises, it's what slides. Deep beneath Sicily, the African plate grinds northward into the Eurasian plate at a rate of several centimeters per year. This collision zone stretches across the Mediterranean, driving earthquakes from Greece to Morocco. Mount Etna sits directly above this tectonic battleground, where continents meet and magma finds its escape. As the African slab descends beneath Calabria, it creates a zone of intense pressure and heat. Mantle material melts, rises, and feeds Etna's constant eruptions. This process has built the volcano over the past 500,000 years, piling basalt upon basalt until the mountain reached its current immense scale. The same forces that created Etna are now destroying it. The subducting plate doesn't just generate magma, it pulls the volcano's eastern flank toward the Ionian Sea. Tectonic stress fractures the edifice from below, creating weaknesses that gravity exploits every single day. Scientists from GeoMar and INGV discovered this in 2016. The volcano isn't just erupting, it's being dragged apart. What holds up a mountain? For most volcanoes, the answer is solid bedrock. Mount Fuji stands on ancient continental crust. Mauna Loa roots itself in the dense floor of the Pacific. Etna sits on something far more fragile. Beneath the volcano lies a thick sequence of marine sediments, clays and muds deposited when this region was seafloor. These soft layers compress and deform under Etna's immense weight, offering little structural support. The mountain essentially floats on a foundation of clay. Offshore, the situation grows worse. The Alto Etna fault system cuts through the seabed east of Sicily, a network of fractures extending 20 kilometers into the Ionian Sea. These faults act like a conveyor belt, pulling the volcano's base seaward at measurable rates. In May 2017, underwater transponders recorded a sudden slip. The seafloor moved 4 centimeters in just 8 days. The entire eastern flank dropped by 1 centimeter during the same period. The mountain isn't rooted, it's sliding. Etna's eastern flank covers 400 square kilometers, an area larger than the island of Malta. This entire mass, rock, soil, lava flows, villages, forests, moves as a single unstable block. Satellite radar and GPS stations track the creep in real time, measuring millimeters of daily motion that accumulate into meters over decades. The movement is not uniform. During volcanic eruptions, the sliding accelerates. Magma intrudes into the flank, inflating the edifice like a hydraulic jack. The added pressure pushes the block seaward even faster, creating a feedback loop that engineers recognize as catastrophic failure in slow motion. Gravity provides the primary driving force, but magma amplifies the effect. Together, they create what geologists call a sector collapse, a process observed at volcanoes worldwide. Mount St. Helens lost its entire north face in 1980. The difference is that Etna's collapse, when it comes, will land in water, and water changes everything. A vast scar interrupts Etna's eastern profile, a horseshoe-shaped depression 5 kilometers wide and over 1,000 meters deep. This is the Valley of the Ox. For centuries, locals assumed it was simply an old crater. Modern geology revealed a more violent truth. The valley marks the site of a massive prehistoric collapse. Thousands of years ago, a section of Etna's eastern flank detached and slid into the sea. The landslide left this enormous depression, a wound in the mountain's side that never fully healed. Seismic surveys of the seafloor east of Sicily reveal what happened to the missing rock. Debris fields stretch 20 kilometers offshore, chaotic mounds of volcanic material piled across the Ionian abyssal plain. The deposits contain tens of cubic kilometers of rock, confirming that this was not a small event. But the collapse left more than rubble.
Research published in 2006 by Maria Teresa Pereschi and colleagues at Italy's National Institute of Geophysics and Volcanology dated the collapse to approximately 8,000 years ago. The volume of material, equivalent to 10,000 pyramids, entered the Mediterranean in minutes. Computer simulations revealed what followed. A tsunami radiated outward from Sicily at 800 kilometers per hour. Wave heights reached 10 meters in the open sea. Within hours, the coasts of Greece, Libya, and the eastern Mediterranean were struck by walls of water that devastated coastal settlements. Evidence of this ancient disaster survives in the geological record. Tsunami deposits called homogenites appear in sediment cores from the Ionian and Sirte abyssal plains, layers of disturbed material that could only result from massive underwater disturbance. On land, researchers found similar deposits along coastlines from Israel to North Africa. One intriguing correlation emerged. The Neolithic village of Atlat Yam, located on what is now the submerged coast of Israel, was abandoned suddenly around 8,000 years ago. No one knows why the inhabitants fled, but the timing matches Etna's collapse with precision. If the tsunami reached Israel, it crossed 2,000 kilometers of open water. Nothing in the Mediterranean was safe. Humans have watched Etna erupt for over 2,500 years. Greek historians recorded explosive blasts that blocked Carthaginian armies. Roman poets described rivers of fire flowing toward Syracuse. In 1669, lava flows buried parts of Catania, the most destructive eruption in recorded history. Each major eruption weakens the edifice further. Lava empties from underground chambers, leaving voids that collapse inward. Magma intrusions fracture the rock, creating new pathways for future instability. The mountain grows and crumbles in a cycle that never stops. In 2021 alone, the southeast crater produced over 50 paroxysmal episodes. Lava fountains painted the night sky, visible from Taormina 50 kilometers away. In February 2022, an explosive eruption sent an ash column 12 kilometers into the atmosphere, forcing Catania Airport to close. The pattern continued through 2024 and into 2025. Between July and August 2024, the Voragine crater produced 6 powerful lava fountain sequences. On January 1, 2026, a flank eruption opened in the Valle del Bove at 2,100 meters elevation. Each eruption is a reminder, the volcano never rests. For decades, scientists assumed magma pressure drove the flank movement. When the volcano inflated, the eastern flank moved. When eruptions drained the system, movement slowed. This model suggested the instability was episodic, tied to volcanic cycles. Everything changed between 2016 and 2018. Dr. Morelia Urlaub and her team at GeoMar deployed 5 acoustic transponders across the submerged southern boundary of Etna's moving flank. Every 90 minutes, the devices pinged each other, measuring distances with centimeter precision. The data revealed something unprecedented. In May 2017, the underwater flank moved 4 centimeters seaward during a period when no eruption was occurring. The movement was gravitational, not volcanic. Magma had nothing to do with it. The entire slope is in motion due to gravity, explained Professor Heidrun Kopp, coordinator of the study. It is therefore quite possible that it could collapse catastrophically, which could trigger a tsunami in the entire Mediterranean. The findings, published in Science Advances, forced a complete rethinking of Etna's hazard profile. The volcano's flank is not responding to volcanic pressure. It is a massive landslide in progress, capable of catastrophic failure with or without an eruption. And no one can predict when. The measurements captured by GeoC transponders revealed that Etna's southeastern flank moves as a coherent block. This is not gradual erosion or small rockfalls. Cubic kilometers of material shift together, synchronized from the summit to the seafloor. During the 8-day slip event in May 2017, onshore GPS stations recorded similar displacements. The entire system, above and below water, moved in unison. This type of coordination has never been observed at any other volcano in the world. The movement occurs along fault planes deep beneath the surface. These faults act as slip surfaces, allowing the block to detach and glide seaward with minimal friction. As the flank moves, stress accumulates along the fault boundaries, building toward eventual rupture. What scientists fear most is acceleration. Small movements measured today could transition to rapid failure tomorrow. Satellite interferometry from the European Space Agency tracks ground deformation across Etna with millimeter precision. Between 2021 and 2024, the data showed persistent seaward motion averaging 14 millimeters per year. That number may seem small, but it represents continuous, unrelenting stress. In 2023, a swarm of shallow earthquakes rattled the southeastern flank. Over 200 events occurred in a single week, clustering along the fault system that bounds the block. Each quake released energy, but also indicated that the system was approaching a critical threshold. GPS stations near the coast measured peak velocities exceeding 30 millimeters per year during volcanic eruptions. The combination of gravitational sliding and magma intrusion creates acceleration that compounds with each eruptive cycle. Meters of cumulative motion have occurred since monitoring began.
The offshore faults show matching acceleration. Bathymetric surveys reveal fresh scarps and fractures along the Alto Etna fault system, evidence that movement is not just continuing, but intensifying. Time is running out. Throughout 2025, Etna's activity reached levels not seen in decades. Between July and August, the Voragine crater produced 6 major paroxysms, each generating lava fountains over 1,000 meters high. Ash plumes rose 8 kilometers, spreading across southern Sicily and forcing repeated closures of Catania Airport. On January 1, 2026, a fissure opened in the Valle del Bove at an unusually low elevation. Lava flows advanced to 1,420 meters, threatening infrastructure and prompting evacuation warnings. INGV scientists noted that the eruption indicated pressurized magma was moving through the system at elevated rates. Seismic data from December 2025 and January 2026 showed sustained tremor and earthquake swarms along the southeastern flank. Ground deformation exceeded previous cycles, with some stations recording displacement rates 50% higher than historical averages. Each eruption adds weight to the volcano. Each intrusion weakens the flank. The cycle is accelerating. Magma does more than erupt. When it intrudes laterally into Etna's flank, it acts as a hydraulic wedge, forcing rock apart and creating space for more magma to follow. This process generates earthquakes, which in turn fracture the edifice further, creating pathways for additional intrusions. The result is a feedback loop. Magma intrusion causes flank movement. Flank movement creates fractures. Fractures allow more magma intrusion. Each cycle amplifies the instability, pushing the system closer to catastrophic failure. Scientists describe this as a self-reinforcing cascade, a process that cannot be stopped once it begins. The only variable is timing. How does a mountain fall into the sea? The process begins with a trigger, a large earthquake, a major eruption, or simply the accumulation of stress beyond the structural limit. The upper section of the flank detaches along pre-existing faults, initiating a rapid landslide. Once movement begins, friction heats the base of the slide, creating a cushion of steam and liquefied sediment that reduces resistance. The mass accelerates, reaching speeds of over 100 kilometers per hour. Billions of tons of rock and debris cascade into the Ionian Sea. The impact displaces an enormous volume of water. A dome of seawater rises 50 meters or more, then collapses outward in all directions. Within seconds, tsunami waves begin radiating across the Mediterranean. The entire process, from initial collapse to wave formation, takes less than 5 minutes. Catania sits 30 kilometers south of Etna's summit, a city of 300,000 built on ancient lava flows. The eastern coast, including towns like Giare, Riposto, and Taormina, lies even closer. If Etna's flank collapses, these communities have no time to escape. Computer models suggest tsunami waves could reach heights of 10 to 20 meters along Sicily's eastern shore. The waves would arrive within minutes, moving faster than any evacuation could proceed. Low-lying neighborhoods, port facilities, and coastal infrastructure would be obliterated. Catania's historic center, built just meters above sea level, would be inundated. The Fontanarossa airport, located near the coast, would be swept away. Hospitals, schools, and emergency services would be rendered inoperable. No warning system can evacuate 300,000 people in 5 minutes. The only option is survival, and even that seems impossible. From Sicily, the waves would spread across the entire Mediterranean. Within 2 hours, the coasts of Calabria, Malta, and Greece would be struck. Within 4 hours, Libya, Tunisia, and the Levant would face inundation. If the collapse occurs in multiple phases, as geological evidence suggests ancient events did, subsequent waves could be larger and more destructive than the first. Secondary landslides, triggered by the initial failure, would generate additional tsunamis with little warning. Rescue operations would be impossible. Ports destroyed, airports flooded, communications severed. The Mediterranean basin, home to over 100 million people, would face a disaster unprecedented in modern history.
And yet, the collapse is not a question of if, but when. The INGV Catania Observatory monitors Etna with one of the most sophisticated surveillance networks on Earth. Seismic stations, GPS arrays, gas sensors, thermal cameras, and satellite radar provide continuous data. 2 volcanologists remain on duty 24 hours a day, analyzing every tremor and deformation signal. This network excels at predicting eruptions. Days or weeks before magma reaches the surface, sensors detect the telltale signs: rising gas emissions, ground inflation, increasing seismicity. Evacuation orders can be issued, tourists warned, airspace restricted. But gravitational collapse is different. It does not require magma movement. It does not produce weeks of warning signals. The collapse could begin with a single earthquake, a structural failure that escalates within minutes. The tools designed to monitor volcanic eruptions may be useless for predicting the mountain's fall. In the best-case scenario, scientists might detect accelerating seismicity hours before collapse.
In the worst case, the first signal would be the landslide itself. No technology currently exists to provide reliable advance warning for this type of catastrophic structural failure. Etna's monitoring network is world-class, but it faces an unsolvable problem. You cannot predict the instant when a crack becomes a catastrophe. Civil protection officials have developed evacuation plans for volcanic eruptions. They know how to respond to lava flows, ashfall, and pyroclastic surges, but there is no plan for a 5-minute tsunami. Emergency systems designed for eruptions assume hours or days of warning. Evacuation routes, shelter locations, and communication protocols all depend on advance notice. When the wave arrives with less warning than a weather forecast, those systems become irrelevant. International tsunami warning centers in the Mediterranean focus on seismic tsunamis triggered by earthquakes. They have no protocols for volcano-generated waves. By the time sensors detect the collapse and issue an alert, the wave would already be approaching shore. The reality is stark. Current preparedness measures cannot protect the population. Over 1 million people live within the potential impact zone of an Etna flank collapse. Catania continues to expand, with new constructions spreading toward the volcano's base. Tourism brings 1.5 million visitors each year, many of whom hike to the summit craters. Economic pressures override risk awareness. Fertile volcanic soils support agriculture across the mountain slopes. Vineyards, orchards, and olive groves climb to elevations where lava flows are a constant threat. Urban development continues in zones that geological maps mark as high hazard. Political leaders face an impossible choice: acknowledge the catastrophic risk and watch property values collapse, or downplay the threat and hope the collapse remains centuries away. The mountain slides a little more each year, and life goes on. Scientists agree on one fundamental point: Etna's southeastern flank will eventually collapse. The geological evidence is clear. The measurements are undeniable. The only unknown is timing. Will it happen in a decade, a century, or a millennium? No one knows. The same gravitational forces that caused the Valle del Bove collapse 8,000 years ago continue operating today. The mountain is unstable now. Etna exists in a geological moment that could last another 1,000 years, or end tomorrow. The volcano does not operate on human timescales. It moves according to forces that predate civilization and will continue long after. What we cannot know is where we stand in that timeline. Mount Etna builds itself through eruption, piling lava upon lava, adding height and mass with each explosive episode. At the same time, it tears itself apart, sliding seaward under the weight of its own creation. This is the paradox of Etna, a mountain that is both monument and avalanche. For the people of Sicily, the volcano represents identity, livelihood, and constant danger. They live in the shadow of a force that gives life and threatens annihilation. The fertile slopes feed families, the eruptions draw tourists. The collapse will destroy everything. 1 million people live on borrowed time, waiting for a mountain to fall. When it does, the Mediterranean will never be the same. How much longer can Etna hold together?